Chapter 10, exercises 1 and 2 are asking you to identify the reactant, that is a Bronsted-Lowry acid and a Bronsted-Lowry base, in a few different reactions. And so the first thing we need to do is to find out what a Bronsted-Lowry acid and base even are. Let's build up by starting with the original definition for an acid and a base. That's called the Arrhenius Definition. So before an acid and a base, acids and bases were ever rigorously defined, an acid was just something that tasted sour. Lemon juice, vinegar, those were acids because they tasted sour. And a base was anything that made something taste less sour. So that was the definition for an acid and a base for a very long time, until around the 1890s, when a chemist named Arrhenius came up with the first rigorous definition. He said, okay, there's a lot of water on Earth, so let's take water as a standard. And here we have our water molecule. You can break water apart into two pieces. So you break that apart. If the electrons go onto the oxygen, then you would have H plus as one of the pieces, and OH minus as the other of the pieces. So this OH minus would go here, and the H plus would go there. And what he noticed was that solutions that had a lot of H plus in them tasted sour. And so he defined solutions that have a lot of H pluses as acids. So acids are compounds that donate H pluses. So if a compound can give an H plus to a solution, then it can make it taste more sour, and it would make it more acidic. For example, here are some examples of Arrhenius acids. HCl, that's stomach acid. How would you ever recognize that as an acid? It has an H in front of it, so it can donate that H and be an acid. Another one, H2SO4, that's sulfuric acid. How would you ever recognize that as an acid? There's those H's in front that it could donate, and so it's an acid. Okay. The other solutions, the solutions that had a lot of OH minus, Arrhenius found made things taste less sour, and so he defined those as bases. So bases, in his mind, were compounds that donated an OH minus. Examples are NaOH, sodium hydroxide, that's in Drano, drain cleaner, or let's say KOH. And you know that you can recognize those as bases without anyone telling you, because they have OHs in them. And a base, according to the Arrhenius definition, is something that donates an OH. So that was the first rigorous attempt at defining acids and bases. But as time went by, people started finding more solutions that either tasted sour or made things taste less sour, but that didn't follow this definition. So they had to come up with a broader definition. And two scientists came up with a broader definition at around the same time. So the second definition, this broader one, that included all these molecules that people were finding, is named after both of those scientists, and it's called the Bronsted-Lowry Definition. They wanted to define acids and bases in terms of things that most molecules have. And so what they chose was a proton. So that an acid, in the Bronsted-Lowry definition, is a molecule that donates a proton. And we'll unpack that a little more in a second. And a base was something that, instead of donating an OH, accepts a proton. So notice how this definition is not as specific. We're not dealing with as specific of things, and so it's going to be broader and encompass more molecules. And that was the reason for coming up with the second definition. All right, let's compare this with the previous one and see similarities and differences. So in the Arrhenius definition, an acid donates an H+. But remember that if you look at the box for hydrogen on the periodic table, there's a 1 above the H. And that means that a hydrogen atom will just have one proton in its nucleus. A proton in its nucleus, and so that it's neutral, it'll have one electron flying around it. But take away the electron, so that it becomes H plus, and all hydrogen is a proton. So the Arrhenius and Bronsted-Lowry definitions for an acid are actually the same. H plus is a proton. And so you can recognize Bronsted-Lowry acids in the same way that you could recognize Arrhenius acids. HCl, how do you know? It has this H, or proton, that it could give away. H2SO4, like we saw, it has those two H's that it could give away. H3PO4, phosphoric acid, it's in Coca-Cola. It has those three H's that it can give away. Where the definitions do differ is in the bases. Now, an Arrhenius base donates an OH minus, but a Bronsted-Lowry base is anything that can accept a proton. What would want to accept a proton? Remember, a proton has a positive charge, and so anything would want to accept a proton that has a negative charge or that has a lone pair of electrons. The poster child for a Bronsted-Lowry base is ammonia, NH3. This is one you would want to sort of keep in the back of your mind. Why would that be a base? Well, remember, nitrogen is in group 5A of the periodic table, so it has 5 valence electrons. We can put one of those around each side before we start pairing them. Hydrogen is in group 1A of the periodic table, so it has 1 valence electron. So notice how you can form this bond between these molecules, and at the top here, you have that lone pair on the nitrogen. That lone pair is a place where there's a lot of negative charge. Electrons have negative charge. And so that would attract a positive charge. It would attract and stick to or accept a proton. So NH3 is the poster child for a Bronsted-Lowry base. But anything that has a negative charge or that has a lone pair would be an example of a Bronsted-Lowry base. So this is what a Bronsted-Lowry acid and base are, and hopefully now we can go back to this question and understand better what it's asking. So it says to identify the reactant, and here they have reactions. You want to divide these reactions into a left side and a right side based on where the arrow is. The left side are called the reactants, and the right side are called the products. So here we're only going to be looking at that left side, the reactants. So they want us to identify the reactant that is a Bronsted-Lowry acid and the reactant that is a Bronsted-Lowry base in each of the following. And to do this, we want to see whether a molecule gives up, accepts, or donates in H+. Okay, so let's start with HI. We'll just choose a molecule and then go to the other side of the arrow, the other side of the reaction arrow, and look for the thing that shares an unusual atom with that, the thing that sort of resembles that. So what resembles HI on the other side? I-. Both of those compounds have an I in them. Okay, when you go from HI to I-, does this compound that you start with gain an H+ or lose an H+? Well, it starts with 1, it ends with 0, it must have lost that H+. In other words, it gave it away. It donated it. A compound that donates an H+, in other words, that donates a proton, because an H+ and a proton are the same, is an acid. And so, HI is a Bronsted-Lowry acid in this equation. Okay, now let's try with the other molecule we have. So, we have H2O. Go to the other side of the reaction arrow and look for something that resembles that molecule. What is it? H3O+. Okay, so this molecule starts as H2O and becomes H3O+. How many H's are in the molecule to begin with? 2. How many H's are in it to end with? 3. So did this molecule H2O that we started with, did that gain or lose in H+? Well, it started with 2 and it ended with 3, so it must have gained or accepted an H+. And a molecule that accepts an H+, that accepts a proton, is a Bronsted-Lowry base. Remember that H+ and proton are synonymous things. So what you would write is that H2O is a Bronsted-Lowry base in this particular equation. And so these two things together would be the solution for that, or the answer for this particular part of this question. Okay, let's try this with the next reaction, B. So we'll pick the first molecule we run across, that's F-. Now, I'm going to divide in your mind the reaction by what's on the left and the right side of the arrow. Go to the right side of the arrow and look for the molecule that resembles the molecule you started analyzing. So here, that would be HF. Both F- and HF have an F in them, so they sort of resemble each other. Okay, so F- turns into HF. Now, you want to see whether this F- accepted a proton or donated a proton. It starts with 0. It starts with 0 hydrogens, 0 H+, and it ends up with 1. So it must have gained an H+, this H, and a plus charge. So it gained an H+. Any molecule that accepts an H+, remember that H+ is the same as a proton. Any molecule that accepts an H+ is a Bronsted-Lowry base. So F- here is a Bronsted-Lowry base. Okay, next. And I'm erasing this just to make more room, but you would want to fit all this work into your page. Okay, so let's look at the other molecule we have, H2O. Go on the other side of the reaction arrow. What resembles it there? OH-. So H2O starts as H2O and ends as OH-. We want to know whether this is an acid or a base. That depends on whether it accepted or donated an H+. H2O starts with 2 H's. It ends with just 1. So it went from having 2 to having 1. Did it accept an H+, or did it give away an H+? If it starts with 2 and ends with 1, it must have given 1 away, or donated an H+. Anything that donates an H+ is a Bronsted-Lowry acid, and remember that H+ is the same thing as a proton. So, what you would write is that H2O here is a Bronsted-Lowry acid. Now notice how whether something is an acid or a base depends on what reaction it's in. In part A, we saw that H2O could act as a base. In part B, we saw that it could act as an acid. It depends on the specific reaction that it's in. So whether something is an acid or a base depends on the context that it's in. In different contexts, the same molecule can either give away an H+, in which case it's an acid, or accept an H+, in which case it's a base. Another thing to note, an important thing to remember, is why this is important. Who cares whether something is an acid or a base? If something is an acid, it will have a lot of plus charge in the solution. So you'd have a lot of H+. If something is a base, you would have a lot of negative charge in the solution. So for example, OH-. And so, Acidity, or basicity, tells you how a solution pushes and pulls, how it squeezes the stuff that's inside of it based on the charge that it has. So, for example, an acidic solution will push on anything that has a positive charge, because like charges repel, and pull on anything that has a negative charge, because opposite charges attract. A basic solution will push on anything that has a negative charge, and pull on anything that has a positive charge. That'll change the shape of molecules, and if molecules change their shape, they'll fit together in different ways, and so behave in different ways. If the pH of your blood changes as much as 1 pH unit, you die within minutes, because all of the molecules in your blood start being pushed and pulled or squeezed in different ways. They stop fitting together with the things that they're supposed to, and then you die. Okay, so let's get back to identifying these Bronsted-Lowry acids and bases in the second example, chapter 10, question 2. So let's pick our first molecule. Our first molecule here is CO3 2-. And you want to divide this reaction based on the arrow. Start with the CO3 2-, look on the other side, what resembles it? And you'll see that it's HCO3-. Both of those molecules have a CO3 in them. So you start as CO3 2-, you end as HCO3-. And we want to know whether this is acting as an acid or a base. That depends on whether it's accepting or donating H pluses. CO3 2- has no H pluses in it. HCO3- has one H in it, an H plus. So the molecule starts from having none to having one. It therefore must have gained or accepted an H plus. And a molecule that accepts an H plus is a Bronsted-Lowry base. So you would write CO3 2- is a Bronsted-Lowry base. And you'd want to keep all of this work here. I'm going to erase it though to make more room so that the explanation will be clear this first time that you're seeing this. Choose the other molecule, H2O. We saw that H2O could either be an acid or a base depending on context. So what is it here? Go to the other side of the arrow. Look for the thing that resembles it. Here that's OH-. So H2O starts from being H2O and it turns into OH-, and we want to know whether it's acting as an acid or a base. That depends on whether it's accepting or donating an H, or an H+. H2O starts with 2 H's, ends with just 1, and so did it donate an H+ or gain an H+? 2 to 1, it must have given one away or donated one. Any molecule that donates an H+ is a Bronsted-Lowry acid. So, you would say that H2O in this particular scenario is a Bronsted-Lowry acid. And these two together would be the answer for this problem. Okay, let's try B. Same procedure. Choose the first molecule. Here, H2SO4. Divide in your mind the reaction into a left and right based on where the arrow is. Look on the other side of the arrow and look for the molecule that resembles H2SO4. Here that's HSO4-. Both of those have SO4 in them. So you start with H2SO4, you go to HSO4, and we want to know whether the molecule is acting as an acid or a base. That depends on whether it's donating or accepting an H+. H2SO4 has 2 H's in it. HSO4- has 1 H in it. So the molecule went from having 2 H's to having just 1. That means it must have given away one of its H's. It must have donated an H+. Any molecule that donates an H+ is a Bronsted-Lowry acid. And so you would write here that H2SO4 is a Bronsted-Lowry acid. Okay, next. Go to the second molecule, and here we have water. Now we saw that water can either act as an acid or a base. It depends on the context. So, what is it acting as here? Go to the other side of the reaction arrow and look for the molecule that resembles it. Here that's H3O+. So the molecule starts as H2O, it ends as H3O+, and we want to know whether it's an acid or a base. So that depends on whether it's donating or accepting an H+. It starts with 2 H's on the left and ends with 3 H's on the right. So it starts with 2, ends with 3. That means it must have accepted an H+. Any molecule that accepts an H+ is a Bronsted-Lowry base. So you would write here, H2O is a Bronsted-Lowry base in this particular example. And those two answers together, those two statements together would be the answer for this question. So, in Chapter 10, questions 1 and 2, you're exploring the idea of what a Bronsted-Lowry acid and base are, and you're using the definitions to identify them in reactions that you may have never seen before. And this is all important because these acids and bases are going to determine how a liquid uses charge to push and pull on what is inside of it.